Have you ever stopped to wonder why brilliant systems, everything from advanced AI to our own brains, can sometimes fail so spectacularly? Well, today we're diving into a new theory that suggests these failures aren't bugs at all, but a fundamental feature of intelligence itself.
So let's start with the central puzzle. You'd think that intelligence should scale up smoothly, right? More power, more complexity, just more smarts. But in the real world, whether we're talking about AI, huge organizations, or even just our own minds, we often see the exact opposite happen. We see a collapse.
And a new idea, called the Unified Intelligence Theory, makes a pretty radical claim about this. It argues that these failures, from an AI hallucinating and just making things up, to a person hitting total mental burnout, they aren't just random bugs. Nope, they are a predictable core feature of how intelligence actually works.
To really get why, we first have to spot a pattern that the theory points out. Think of it like a ghost in the machine that shows up across all kinds of intelligent systems. It's this consistent signature of failure, and it's been hiding in plain sight this whole time.
I mean, just look at the range here. An AI model that starts contradicting itself, your own brain feeling totally overloaded, a huge company getting tangled up in its own rules. It all looks so different on the surface, but the underlying pattern is the same. Intelligent systems don't just grow and grow smoothly. They often hit a breaking point and become really, really brittle.
So the theory suggests there's one single process behind all these different kinds of failures. And here's the kicker. It's the very same process that makes these systems intelligent in the first place. It's both their engine and the source of their downfall.
The theory calls this core engine recursion. Now, this is more than just a simple loop. It's a system's ability to turn back on itself and actually change its own rules. It's literally the process of thinking about your own thinking. This is the engine of all learning, but as you might guess, it comes with a really dangerous side effect.
And here is the catch. When a system thinks about its own thinking, it amplifies everything. Not just the good ideas and the insights, but also every tiny little error, every inconsistency. So the deeper the thought process, the bigger the potential insight, sure, but also the bigger the potential mistake.
So if recursion is such a massive double-edged sword, how does any intelligent system manage to stay stable? How does it not just fly apart? Well, the theory gives us a really elegant answer. It's all a constant dynamic balancing act.
Okay, now this is where it gets really cool. The theory splits this whole process into two states. You've got function, which is the live, messy, active pressure of trying to solve a problem right now. And then there's form, which is the stable memory or the rule that gets created after a solution has been found.
And a simple traffic light illustrates this loop perfectly. You start with total chaos at an intersection. That's pure function. It's a contradiction that needs solving. So a solution is proposed, a rule. A traffic light gets built. That's the new form. A messy problem has been compressed into a stable physical structure. And from then on, that form, the light, regulates all future function, creating order out of the chaos. And that's the fundamental heartbeat of intelligence. The messy, active process of thinking creates a stable structure, like a memory or a rule. And that structure then turns around and guides the next messy, active process. It's just this constant, evolving dance. But of course, a brain can't build a physical traffic light inside itself. So how do really complex systems handle more and more pressure without just collapsing under the weight of their own thinking?
Well, they do it by offloading their work onto external structures. The theory has a great name for these: functional intelligence relays, or FIRs for short. You can think of them as memory scaffolds that get built outside of the main system.
And these fires are literally all around us. Language lets us store and share incredibly complex ideas so we don't have to reinvent them every single time. Written laws store the solutions to social problems. Computer code stores complex logic. All of these things are basically external hard drives for our collective intelligence.
So, at the end of the day, intelligence doesn't just scale by getting bigger on the inside. It scales by building a brain outside the brain, this whole external scaffold of solutions that it can rely on to avoid total overload.
So now we've got this complex system of internal thinking and external memory. To really make sense of it all, the theory gives us more than just concepts. It offers a whole new language, a map for charting the stability of any intelligent system you can think of. It actually introduces a formal vocabulary to describe all these forces. Entropy is that constant pressure of disorder. Compression is that magic moment of creating a clear rule out of chaos. And collapse, well, that's total system burnout. This gives us a practical toolkit we can use to diagnose the health of any system, from a single AI to an entire economy.
And that right there brings us to the ultimate takeaway. This theory suggests that maybe we've been thinking about intelligence all wrong. Maybe it's not a race to see who can build the biggest, most complex recursive engine. Maybe it's about getting better at the delicate art of balancing creative chaos with stabilizing structure.
This reframes the entire goal, not just for AI, but for how we build our organizations and even how we think ourselves. And it leaves us with one last, really provocative question. If the goal isn't just growth, but balance, what's the end game for intelligence?